In this video, I will be discussing a helpful approach for Bayesian data analysis, which I'm calling telling a data story. So what is a data story? Basically, it is just a story for how the data came to be, and it could be descriptive based on associations between variables, or it could be causal, based on, X causes Y. If I eat, I am full. It should describe the underlying reality of the system as well as the sampling process for how the data came to be. And most importantly, for Bayesian data analysis, this provides the basis for how we simulate new data and perhaps describe perturbations to the system. So I did not make up this data story concept. I learned it from Richard McElraith in the Statistical Rethinking book and series of lectures, which I highly recommend. I found it helpful for getting me to think more holistically about data analysis and lead with my scientific understanding and rather than getting too stuck on the statistical minutia. So my objective for this lecture is to give you a preview of the data storytelling process as it might be done for a Bayesian statistical analysis. No actual Bayesian stats here yet. So this is just telling a story about how the data came to be, translating that story into a generative model, using that generative model to simulate data, which I provided some sample R code and exercises, and predicting how the system will respond to change. But in order to do that, I want you to understand what it means for a statistical model to describe a data generating process as opposed to describing a data set. So if you've had some stats education, you might have to unlearn a few things. So when we're describing data, one way we can approach it is to think about its shape. So anytime I get a new data set, I'll make a plot like this where histogram where I split up a variable into bins, count up the number of individuals in each bin. This is a data set from the US Bureau of Labor Statistics of height in adults that I'll be using to illustrate throughout this lecture. If we divide the number of people by the total, we can get the shape of the data regardless of sample size. And now you'll notice that the y-axis now says density instead of count. And that's because this relates to the term probability density in statistics, which is basically just how likely it is for a random variable to be a particular value. So higher means there's more people, a greater proportion of people in this range than in this range, so it has a higher probability density. So another way, besides thinking about the shape, oh yeah, by the way, so this important part of this density is that it sums to one, which is important for all the math. So in addition to describing the shape, we can describe data in terms of summary statistics that tell us about key characteristics. So in any continuous metric variable like height, we'll probably have some metric of central tendency and some metric of variability, which I'm showing here as the mean and standard deviation. And it just so happens that these two ways of quantifying these characteristics relate to the normal distribution model. So um, in uh, word as a sentence, you would say height is a normally distributed random variable with a single mean and standard deviation. On the right is how you'd say it mathematically. So mean is often represented as a mu, standard deviation off as a sigma. And now I've drawn the blue curve here showing the probability density of this model observing value x under this normal model. And just as an aside, R has inbuilt functions for dealing with these standard distributions, such as the normal distribution. I've put a link that provides more information about them, but there's usually DPQ followed by a code for the distribution, in this case normal. So this will be useful for dealing with theoretical distributions. And there's also inbuilt ones for, common metric data, binary count data, etc. So just an aside. So now I want to shift gears from describing data to describing how data are generated. So we have the same data set, US adult height, but now I want to tell a data story for how these data came to be. So we know that people grow up to adulthood and they reach a certain height. Some people are taller, some are shorter, and most people are somewhere in the middle between very tall and very short. So this describes how each individual height data point might exist, and we can translate this into that same model we were looking at before. So um, aspects of our data story correspond with aspects of the model. So we've got a random variable height that has some variability described by sigma, some central tendency described by mu. And what's really helpful about this this framework is that now that we have a generative model, we can actually use this to simulate new data. So I just want to introduce you to the um, inbuilt sampling functions in R. So this is a R norm is the function. We have a number of samples. We've got a mean, a standard deviation, and we can use this to generate independent, identically distributed samples. And then values with higher probability density are more likely to be sampled. Just to illustrate this, I did a simulation of this model with 10, 100, 1,000, 10,000 samples. And you'll notice that as we get more samples, our simulated data becomes closer and closer to our theoretical distribution. And this might seem kind of silly when we're just thinking about a really simple model like this, but this is actually the theoretical basis for Monte Carlo sampling, which is how Bayes works. You know, if we can't estimate a parameter mathematically, we can approximate it just by sampling on these distributions again and again. So just to recap, we've observed some data, we told a story about how that data came to be and translated that story into a generative model, simulated some data using that model, and then what we could do next is compare the observed and generated data to make inferences about the system. And so this is an example of a sort of one iteration of what we might go through in a Bayesian data analysis workflow. So if we go back to our data story and look at our model, in addition to telling our story in words and variables, we can also draw diagrams that tell us, you know, about the factors that are influencing our variable height. But you might notice that something is missing. So, all right, yeah, so say this. So the idea of a causal diagram, I'll discuss in another lecture, but I find it useful. So the missing element, you can probably guess, is that sex is missing. So men and women tend to have different heights. So we can go back to our data story and revise it to put in this missing piece. Women and men have separate heights, which we can represent, you know, with our separate mean and standard deviation parameters for men and women. And then in the population, there's going to be a proportion of women and men, and that proportion is going to affect the overall height distribution. So that parameter I'm calling phi. And then the new model looks like this. So we have our random variable height is a Gaussian mixture of women and men. Here there's two groups, so the proportion of men is 1 minus phi. Um, and I've plotted that using the theoretical distribution functions in R. Code is in the code. So might notice here this red line seems to be a much better fit to the shape of our distribution than this blue line is. So if we were just using a purely descriptive framework, we might say that we reject model 1 in favor of model 2 because it's better fit to the data. And we can do some kind of goodness of fit test, but it would tell us what we can see with our eyes. But in a generative mindset, we might say that model 1 describes part of generative process in model 2, and both models are useful for understanding our system. So my main point here is that we often need multiple models to tell complex data stories about complex systems, and we can never, we can never get the whole picture in one model, but it can be useful to have simple models that help us to elucidate aspects of the story that we're interested in, and often more than one. So moving on to the idea of prediction. And this is the last thing I want to emphasize that a key benefit of this generative model framework is that it allows you to make predictions about how a system will change, or perhaps make inferences about missing data. So in this example, like we have our model and our data story. Let's say we have a scenario where there's an influx of Amazon warrior women. We could simulate that by increasing mu W. We have, people randomly eat and drink potions that make them larger or smaller. We could simulate that with an increase in the standard deviation, sigma. Or, maybe a lot of men have decided to leave for whatever reason. They got scared. So we could simulate that by increasing the proportion of women in the population, phi W. So these are silly examples, but just want to use it to get you thinking about models as a generative tool. So I've included some exercises in the lecture code to give you some practice using these R tools and writing code to do basic sampling tasks. So, okay, in closing, I will recap. So, this process, we tell a story about how our data comes to be. We represent that story with a model, and oftentimes the model will have some combination of random variables, probability density function, probability distribution functions, parameters, and we use our model to generate data, and there's good inbuilt sampling functions in R to do that. And then we use the model also to predict how a system will respond to change and perhaps investigate various scientific questions. So that is it. I hope you find this helpful and that you enjoy the exercises. All right, thank you.